My name is Andrew Kennedy. I usually go by Kit, so feel free to call me that. But I'm going to be talking to you today mostly, or a fair bit, on the flight software architecture for our CubeSat named MiRaTA. But I'm also going to be talking a little bit about another topic as well, which I've incorporated in here, scaling CubeSat flight software to cooperative constellations. So I'll just leap right into it. First, I'm going to talk about my purpose and motivation, and then the MiRaTA flight software architecture, and scaling up to a CubeSat constellation, and finally my conclusions. So the purpose and motivation for this talk is twofold. First one, like I said, introducing our CubeSat flight software design. So this is a small satellite, but it has a complex mission, as you'll see. And I want to identify some of the benefits and limitations of CubeSat-oriented flight software. And then I'm going to discuss initial work on scaling the flight software up to a distributed constellation architecture. So enabling cooperative operations, specifically observations in a remote Earth remote sensing constellation. And then maximizing autonomy and activity planning. So going into the MiRaTA flight software architecture. This mission is, first of all, the acronym stands for Microwave Radiometer Technology Acceleration CubeSat. We're funded by NASA ESTO, so the Earth Science Technology Office, as well as NOAA. And our launch is in early 2016, so we're building it now, and we just got through PDR, actually, this past October. It's a follow-on mission to a previous CubeSat that we built that's currently on the ISS, waiting for deployment. There's been some difficulties with the deployment mechanism. That wasn't ours. And so that's kind of held things up, but that's in the works now, and it should deploy early next year. So what the micromass CubeSat did was it had a rotating radiometer payload that basically scanned the Earth below and then looked into to deep space. I'm going to use deep space as a kind of calibration target. What MiRaTA, this new CubeSat, is doing, the picture is there in the bottom right, is taking that radiometer and fixing it on the bus so it no longer rotates, but we're also adding another instrument, a GPS receiver for GPS radio occultation measurements. And I'll explain a little bit what those are on the next slide. But the important part to get here is that the radiometer instrument just looks down at the Earth, like a volume of atmosphere below the CubeSat. And then we use GPS radio occultation measurements for calibrating the radiometer. And it's basically testing a new method for calibrating radiometers, because normally they have internal calibration targets that drive the design of the system, and we're trying to kind of get rid of that. The developers are MIT campus. We're developing the bus. MIT Lincoln Lab is working on the radiometer payload, as well as kind of space vehicle integration. The Aerospace Corporation is on the GPSRO payload, and then finally UMass Amherst and Space Dynamics Laboratory are helping with the mission. So the MiRaTA space vehicle itself looks like this. The top part is the payload. We have a tri-band microwave radiometer there at the top, and then a patched antenna array for the GPS receiver on the back of the satellite, which I guess I don't have a great picture of right now. But the bus is composed of an avionics stack, including our UHF radio, a spring tape antenna, our Pumpkin PIC24F motherboard, which I'll talk a little bit more about later, but an EPS battery, and some custom interface boards. And then we have deployable solar panels, and finally basically a unitized ADCS module from the Maryland Aerospace Incorporated. Basically has reaction wheels, torque rods, gyros, Earth horizon sensors, sun sensors, all kind of incorporated into one unit. So it reduces kind of the complexity of our development process for the bus. So I wanted to touch on what GPS radio occultation measurements actually are. And this is kind of a good illustration of it. And basically, if you imagine that we're the satellite there on the far right, no, it doesn't look like a CubeSat, but imagine we are. We are looking at signals coming from a GPS satellite way in the distance in MEO somewhere. And those signals are passing through the Earth's atmosphere. And as they do, they're basically affected by the refractivity of the atmosphere. So if you have precise timing, which you do because you're getting a GPS fix from your GPS receiver, then you can determine from your spacecraft when you see those signals kind of a refractivity profile through the Earth's atmosphere. And that gives you information about temperature, pressure, volume, that type of thing. And you can use that as calibration for the radiometer instrument. And the way we actually do this calibration on MiRaTA is with this slow pitch-up maneuver. So basically, you can imagine that we're coming over, we're coming from the left here, and that first step, we're just looking at the Earth's atmosphere with the radiometer, and then we slowly pitch the spacecraft up, and as we pitch up to that final 110 kind of nominal degree pitch angle, we look back through that same volume of atmosphere with the GPS RO instrument. So we're looking through the same volume atmosphere. We looked at it with the radiometer, looked at it with the GPS RO measurements. We can use it as a calibration source. This whole maneuver takes about 20 seconds, and it has a 0.5 kind of nominal degree per second rate. So this is kind of a complex maneuver for such a small satellite, and it's I think one of the most complicated things I've seen on a CubeSat to date. So this is designing for this maneuver is kind of part of the what we have to consider in the flight software design for our spacecraft. And I just kind of wanted to talk a little bit about the concept of operations for how the spacecraft will work and how that maneuver kind of fits in. So we have a launch via the Educational Launch of Nanosatellites program through NASA. And that should be in early 2016. We're going to be in a 600-kilometer altitude sun-synchronous orbit. So that's our release, basically. So while we're stowed on board the rocket that will release us, we basically the spacecraft is not on. And we have an early orbit activation phase where after we deploy from the spacecraft, the flight software turns on, and then we have to wait for 45 minutes before we can actually start communicating and deploy solar panels. This is kind of standard for the way CubeSats work. They have just like that limitation. And then we start our science operations. And our goal is to execute one of these calibration maneuvers that I just showed per orbit over a 90-day mission. And we currently only actually have one ground station that we're at least using for the micromass mission, and that's kind of our baseline for this now new MiRaTA mission. So we only have commanding at a certain time during the day, and then we have a gigantic blackout period where we can't communicate. So that need to actually be able to execute these maneuvers once per orbit during times that we haven't had communications, say, for up to 15 hours or so, has kind of significant implications for how we're going to actually operate the flight software. And I guess I have some information down there below about our radios. The important point is just that when we have our ground station in sight, we have a 1.5 megabit per second downlink rate. And then we have a kind of secondary beacon that is just always actually sending packets through the global star constellation, which is it's kind of nifty for a CubeSat. And this is our early orbit activation sequence. We're going to be deployed from a P-pod orbital deployer. And then during this initial phase, we have to inhibit communications, and we can't basically do anything with the spacecraft. And then we actually deploy solar panels and can start communicating. So this process going from inhibit to deploy after we release from the P-pod is just totally automated. So we deploy solar panels using thermal knife devices, basically a burn wire. And then after we've deployed our solar panels, we go to a safe mode. Basically, the spacecraft just waits for an uplink from the ground to tell it to enter science operations. And then the way our nominal kind of modes look, we start out in that safe mode, and then there's a ground command to transition to the normal kind of base operations mode for the spacecraft. So that's kind of what we come back to whenever we're not actively doing a calibration slew maneuver, or we're not downlinking to the ground station and such. Then we can do downlinks to the ground station. They're about 10 minutes. And that's initiated by a ground command from the ground station. And at the end of downlink, we transition back to a normal mode. Then we can do a maneuver. So this is basically we uplink a command in advance to the spacecraft to tell it when we want it to do this maneuver. And like I said, this could be at the end of a kind of a communications blackout period. So you can imagine that we have kind of a queue of maneuvers, or a queue of commanded maneuvers that the spacecraft is waiting to do at any given time. But when it starts a maneuver, it just transitions this mode, and then it takes about 20 minutes, and it ends up back in normal mode. Then finally, because our spacecraft is not power positive in normal operations, we have to have a battery charging mode where we just point directly at the sun. And we don't have any gimbaled solar panels because it's such a basic satellite. So we actually have to do coarse pointing, point the whole satellite at the sun. And finally, at the end of life, we have a decommission mode. This slide just kind of summarizes our notion of how we transition between these modes. We can do a maneuver and then kind of have a normal mode. And finally, maybe we'll have a downlink and then another normal mode, then battery charging. And then that's on a typical science orbit. And then maybe on a typical non-science orbit, we have battery charging, normal, downlink, battery charging again after that. So the implementation of all this is going to be on a PIC24 microprocessor, which is fairly, it's I guess fairly simple as far as microcontrollers for spacecraft go, or processors for spacecraft go. We're getting both the processor and motherboard from Pumpkin Incorporated, which is a big kind of CubeSat part supplier. It's a 16-bit processor running at 16 MIPS. It has 256K of flash program memory, 96 kilobytes of data memory. So it's fairly limited. We're actually building the flight software entirely in C, and we don't actually have like a Linux distribution or anything on it. It's just all kind of a monolithic program. We're using a very basic real-time operating system called Salvo. It's basically a minimal memory use RTOS. So it's cooperative multitasking. When we have multiple threads kind of running in parallel, and whenever one thread finishes with, or a task, I should say, whenever one task finishes with the computations it wants to do for a given cycle, it says, well, I'm done for now, and another task can take over execution at this point. Yeah, and that RTOS provides some basic intercommunications, resource management, et cetera. And the way our flight software architecture looks at this point, I'll just kind of step through. So this is basically a diagram that includes a lot of our tasks in the flight software. So we have this kind of central set of tasks that handle the kind of the high-level management of the spacecraft. So we have kind of a basic startup code, but then we have these three main tasks: housekeeping, the mission manager task, and a command handler task. So the mission manager task is responsible for implementing that state machine that I showed earlier. So the different operational modes, as well as commanding the payload to do what is necessary, as well as the ADCS to do slew when necessary for our calibration maneuvers. The housekeeping task there at the top left just collects telemetry and packetizes that and gets that ready for downlinking to the ground, as well as assesses that telemetry and looks for faults to see if the watchdog timer needs to be petted, as it were. And then we have our command handler task here at the bottom, which is responsible for accepting packets that come from our radio driver task, and figuring out where those commands should be put kind of on the queue. If there's a kind of a preemptive command for like entering safe mode, then that might be executed immediately. Otherwise, as I mentioned before, we have comm blackout periods. We might need to schedule multiple maneuvers in advance for all the orbits during that blackout period. So we have a queue basically where we're storing. It's basically a schedule for what modes we want to execute at given times up to a certain kind of planning horizon in the future. Then we have an ADCS manager task that is in charge of communicating with the Maryland Aerospace ADAX unit. Basically collects telemetry from the MAI, as well as collects telemetry from the gyro. And we've implemented a Kalman filter and control law and everything just kind of in flight software, totally in C within our flight software implementation. Then we have some more tasks that handle the primary radio as well as the backup radio. A payload driver task that interfaces with our payload. And I guess I should call out that the mission manager has to manage that ADCS manager task as well as the payload driver task during a maneuver. And finally, some more tasks for like the thermal knife drivers for deploying solar panels, power distribution units, EPS, and then temperature sensor devices. So that's kind of what the flight software architecture looks like at a high level. So this is a slide on our current state. I guess I'll just mention first off that I didn't dive into a lot of detail on how the software looks at this point because we're still at an early stage. As I mentioned, we passed PDR, so a lot of what we've done so far is architecting the system and making sure that we'll be able to fulfill all of our requirements. And at this point going forward, there's a lot of coding to do. Fortunately, we have a lot of heritage from the previous CubeSat that we built. MicroMass, they did a lot of driver development for that. A lot of making the basic hardware interface that was on the system. And we're inheriting a lot of that, which is fortunate. Of course, we inherit the problems with that too, which weren't totally ironed out because on such a small program, or I guess on most programs, you get towards the end and you don't have the time to iron out all the problems in the software. And then we're adding, on top of that, the difficulties of scheduling these maneuvers during COM blackout periods, as well as more robust fault handling, which we still kind of have to get into designing, as well as reprogrammability. So just hitting on the benefits and kind of limitations of this flight software implementation. One of the benefits, I would say, is the kind of the simplicity of it. For more complex spacecraft, I think there's a lot more considerations that have to go into the design of the flight software for like an orbital insertion activity. But our spacecraft is kind of an always-on. It does science whenever that is available, and then the rest of the time it kind of waits for a downlink. There's no kind of critical. There aren't very many critical phases that we have to go through, so that kind of simplifies. That kind of lends itself to a high level of automation. But some of the limitations here are little processing power with the PIC-24, and that we're kind of unable to do complex activities because of that processing power. And that's kind of a direction that we want to head in the future, actually using a more capable processor and putting a Linux distribution of some sort on board. So that was my kind of coverage of the flight software architecture for MiRaTA. And now I'm going to talk a little bit about how we're using that as, or I want to use that as inspiration for scaling up to a constellation of CubeSats. So this first slide, there's a lot of detail on it, but I'm basically calling out the kind of the motivation for why you want to build a coordinated constellation. What I'm thinking about specifically is kind of remote sensing science applications in low Earth orbit. So there's these kind of sample cases here on the right. In A, you might have two spacecraft with similar payloads, with similar instruments that are observing kind of the same volume of atmosphere. And they can look at that volume of atmosphere at the same time, and two sources of measurements are better than just one. And B, this is kind of the MiRaTA application, where you have one instrument that is being calibrated by another instrument. And then C is a case where you have multiple different kinds of instruments that are all observing at the same time, and kind of adding a lot of synergistic information in that way. Another potential benefit of constellations is spontaneous observation opportunities. So basically, if you have a spacecraft in one part of the constellation that sees an interesting event in the Earth's atmosphere, maybe a weather system of some sort, then it can notify other satellites in the constellation about this interesting opportunity, and they can follow up immediately without having to necessarily talk to the ground. And then there's, on a constellation, you could have more effective downlink to ground stations by using it as kind of an ad hoc network, routing data through the constellation and and basically reducing latency by forwarding information to the CubeSat that is closest to a ground station at a certain time. And so kind of the goal is to exploit the simplicity of a kind of MiRaTA architecture, that simple state machine, and scale it up to a distributed constellation of simple satellites with heterogeneous payloads. But some of the challenges with this are, first of all, limited communications access to spacecraft, so communications backup periods, like I mentioned, and bandwidth limitations. If you want to launch, say, 100 spacecraft in a constellation, which might not be too far out, then you're not going to have just infinite ability to communicate because of spectrum allocation limitations. If you want to actually coordinate these kind of, the second point, if you want to coordinate these calibration activities, say if you were using the MiRaTA concept of operations, you have to consider kind of tight onboard, tight activity coupling between all the spacecraft. So if spacecraft 1 wants to coordinate something with 2, 2 with 3, 3 with 4, et cetera, going forward in time, then if there's a problem on 1, that might affect what 2 wants to do, which might affect what 3 wants to do, et cetera. And how do you inform between these spacecraft that a plan update is necessary? There's limits on ground control interaction, so if we have this many spacecraft in a constellation, how do you actually have, you can't really have infinite human operators looking at, or doing sequencing, and looking at faults that emerge on these satellites. And then finally, spontaneous events. If an event appears, or if a new observation, interesting observation opportunity is spotted by one spacecraft, then how does it kind of reconcile that high priority observation with the previous plans that all the other spacecraft are currently planning on doing? So I've kind of identified a need for onboard software to autonomously coordinate observations with as little grounds in the loop, with as little ground in the loop as possible. So in order to actually kind of solve this high-level problem of how you coordinate all these operations on a constellation, I think we need to simplify the problem first. So just kind of considering activity on board only 2 spacecraft. So I'm looking at a 2-agent scenario, kind of very simplified here into kind of a hardware and software testbed, in which you have basically what I'm calling spacecraft agents in the middle here, which are just kind of webcams on a motor that kind of slews around. And you can look at targets. In this scenario, there's a reward for looking at targets jointly. So the 2 agents are kind of looking at a target at the same time, and that is kind of a proxy for a coordinated observation in Earth orbit. Looking at a target generates data that you have to downlink. So there's a ground station target that they can look at. And then all these activities take up energy. So there's an energy source that you have to look at to regenerate energy, effectively. And each of these agents has kind of a notion of an onboard state that includes energy storage, so like battery level, data storage, and momentum storage, so angular momentum storage, kind of a proxy for reaction wheel angular momentum storage. And then the software on the 2 agents that plans their individual activities can cross-link with each other, can talk to each other, to share state information, as well as their plans for activities in the future. But the problem with a real constellation is that you're going to have limited cross-link availability due to orbital geometry constraints and bandwidth constraints. So there's sporadic availability of this cross-link. So I'm designing an agent software that goes on both of these these 2 microcontrollers controlling these web cameras, so that it can maximize the amount of joint observation of targets while minimizing the staleness of shared state information between these 2 agents. So now considering planning on board, so given an initial plan of when you want these 2 agents to do a coordinated activity, and when they want to do a coordinated activity, how do you actually plan all of the activities that a single spacecraft or single agent needs to do in order to meet its onboard resource constraints? That's kind of the part that I've started with now. So to I guess give some background on how that's formulated, this is a state or a mode diagram or state machine for the operations of a single one of those agents. The activities at the top are basically these reward activities. There's target observation, that's when it's looking at one of those targets that I showed, and crosslink, which gives state updates. So basically you want to spend the most time in a target observation mode and minimize the time between a target observation and a crosslink to minimize that state, the staleness of that state information. These activities at the bottom are management activities. So desaturation reduces stored angular momentum. Downlink reduces stored data, and recharge increases stored energy. And then finally, these two modes in the middle, slew is a way of representing that you have to, your spacecraft will be pointed at different attitudes for all these different activities. So you have to slew between different modes. And then idle is a lower resource utilization mode that kind of, you can serve as a fill-in. So an example of kind of resource utilization and target observation, this is similar for kind of the other modes, is that you might have a power draw of 12 watts and a data rate of, or producing data at 35 kilobits per second and producing momentum at 20% every 15 minutes, at 20% of maximum storage. These numbers are based on actual numbers from the MiRaTA spacecraft mission. So you can generate, given the observations that you want to do and the availability of observations due to orbital geometry constraints and the availability of crosslinks, you can generate kind of an initial plan. So this is just showing for a single spacecraft agent in this demo, consider when it can observe and when it can actually crosslink with the other agent. So these are kind of the windows that it can do that. Then I'm adding in the times that it can actually downlink to a ground station and when it can recharge, that purple line. I probably should have had arrows pointing specifically what these are. But you can generate an initial plan of activities for a single agent. In this case, we just want to, the black line represents the initial plan. We want to observe when we possibly can, want to do a crosslink whenever we can, and then we have a slew mode between an observation and a crosslink, and just idle modes to kind of, as placeholders the rest of the time. So given this initial plan, you can introduce gradually other activities that are necessary to meet onboard resource utilization constraints. Again, that's energy, data, and angular momentum storage in this first formulation of the problem. And that's, so I'm introducing a mixed integer linear program to solve that. This line at the top is an objective function that basically in layman's terms, I'm trying to maximize the amount of time that one of these agents spends observing, so it spends in its observation modes, and minimize the time between a crosslink and an observation. Again, to keep state information as, to minimize the staleness of it. But maximizing this function is subject to several constraints. First of all, that activities have to follow each other, and they have to start at time 0 and end at a horizon, a time horizon of planning. And then observation timing, say for example, observation timing has to fit within the windows that observations are actually available to be executed. And the same kind of goes for downlink, crosslink, and recharge. And then the spacecraft agent has to respect upper bounds and lower bounds on its resources. So this is just formulated in terms of energy storage. It has to maintain its energy storage above a lower bound at all times, so it's battery level below and lower bounds, and above and lower bounds, and below and upper bounds. And the same goes for data storage and momentum storage. So that's a lot of equations, and it might be kind of difficult to fully ingest all that just looking at the slide. But I have an example on the next slides of kind of how this works. So the way we want to do it is take an initial plan of activities that's there at the top. That's just the same that I introduced on a couple slides previous. And you see that given that initial plan, resource utilization on this single spacecraft agent doesn't stay within bounds. So that blue line for energy storage at the top goes out of the red lines that are bounds on it. The same with data storage and the same with momentum storage. And it makes sense. Energy storage, energy is taken up as you do these activities. Data is produced as you do these activities, and angular momentum is produced as you transition between these activities. So we want to, first off, say, meet data storage requirements, because the windows for data for downlinking to the ground are so limited. So we introduce, say, a downlink activity in this first window for downlink. Hopefully you can see that downlink window, that blue line. When we introduce that, all of a sudden our data storage resource utilization looks a bit better. We're not going out of the limits as much as possible, but we're still not quite meeting it. And note again that I'm solving the mixed integer linear program again. I'm just enforcing the constraints on data storage. And so the program is trying to meet those constraints while also trying to maximize observation timing and minimize, again, the time between crosslinks and observations. The only problem is that even with totally minimizing the later observation times, like not even really doing an observation, too much the data storage limitations cannot be met. So let's try introducing a second downlink activity. And now all of a sudden data storage constraints can be met, and we have a consistent plan. So we've solved the mixed integer linear program consistently. But we're still not quite there in terms of energy storage and momentum storage, so we add recharges. We're getting a more complicated plan, but now we meet both energy storage and data storage requirements. And then, satisfying the last constraints, we can add desaturation activities, again, to get rid of stored angular momentum. And now we have a plan for a single agent's kind of timeline of activities that meets all resource constraints, and it's able to do those observations when at the times that it negotiated with the other spacecraft agent, and it's able also to cross-link with the other spacecraft agent to reduce uncertainty in terms of its estimate of the state of the other agent. So we're done. And that was kind of that was the first step in actually doing the planning process for a single agent. And my next steps are to actually incorporate that in with an algorithm that negotiates the timing of observations and crosslinks between the two spacecraft. So basically, searching a giant tree to see where the optimum point is for the number of observations and number of crosslinks that can actually be done in a certain planning timeline. So concluding, as I said, there are two distinct sections to this presentation: the MiRaTA CubeSat software architecture section and the planning algorithm for a single spacecraft kind of scenario in a coordinated constellation. And they might seem kind of distinct, but it's kind of a natural combination, I would say, because the CubeSat flight software architecture, with its kind of its simplicity in terms of modes and transitions between those modes, lends itself to a kind of a high-level algorithm for autonomously coordinating operations on board a constellation. And future work for me involves bringing kind of these two things together, actually implementing that in a real CubeSat flight software architecture. So that includes more precisely modeling real resource usage on board a CubeSat, figuring out how to plan coordinated activities between spacecraft, and then testing in a multi-agent simulation. But meanwhile, work on the MiRaTA flight software continues, and delivery of the actual spacecraft is at the end of 2015 for a 2016 launch. And just quick acknowledgements. First of all, Ryan Kingsbury, who wrote a lot of the code for MicroMass, the preceding CubeSat. And then the teams on MIT campus and Lincoln Lab, the sponsor at MIT Lincoln Lab, and then finally the National Science Foundation. Thank you. And if there's any questions, yeah.
Impressive. First of all, do you plan on revisiting design and development when MicroMass has been deployed and you have some results?
Yes. Yeah, I definitely want to do that. Because
Is that in the schedule?
the schedule for the work on the... Oh, sorry. Oh, yeah, sorry. I need to talk in the microphone. The schedule for... so the question was, do I plan on revisiting based on MicroMass operations information, what I want to do? And you mean in terms of the schedule for my work on coordinating constellations or on MiRaTA? Okay. Yes. So that is part of the plan, that we want to take our basically the lessons learned from operations on MicroMass and plug that into the actual code for MiRaTA. I think that's mostly going to manifest itself as fault handling a lot, because the fault handling on MicroMass was fairly simple. We didn't have a lot of time to develop that code fully, and I think we'll learn some very valuable lessons from how it operates, and we can fold that into the MiRaTA flight software. Yeah.
This is a continual problem in CubeSat and universities, because typically the developers, the students, have graduated before the device is ever launched, so we don't have any lessons learned.
That's true.
Sometimes the universities lose interest in the device at that point because nobody's building it.
Yeah, that's a good point.
So you plan on being around. What year are you?
I'm a second-year master's student, so nominally I could graduate, but I want to go for a PhD, so it quals is in January, so hopefully I'll be around. Yeah.
Now, focusing on the swarm, on the constellation you're looking at,
Mm-hmm.
do you have any dates already scheduled for that?
At this point, I don't have any dates for when I'll actually be able to implement this on a real CubeSat platform. I mean, of course, I'm still at the kind of early stages, but we can't do it on MiRaTA just because we've baselined this simple processor, the PIC, and it just doesn't have the computing capacity for doing this, for solving a linear program. But I think that the next iteration, the next CubeSat that we build, will be able to actually implement something like this. That's my hope. So, yeah, I hope so. Yes.
Oh, you know what? If you're going to do that, let's use the microphone because we want to record it. No, you're not. No. It's digital recording.
And that was going to be my question. If you were going to implement any of this algorithm, any part of it on MiRaTA, since you're already thinking about it, but you don't think you have the processing power for that.
Yeah, I don't think we have the processing power for it.
Okay.
I haven't looked into it seriously, but it seems like orders of magnitude difference in terms of the processing power. Yeah.
No, and to answer your question, we too at the University of Colorado have been working on CubeSats, and you're right, there is a problem with passing on that knowledge and keeping the students long enough to see the program through. So what our solution is to make sure they have professional mentors who are there, understand the project, so we can work with the next generation of students and keep the interest going and keep the project going.
Makes a lot of sense. And we have that a little bit with Lincoln Lab, I should mention.
Can you just give an estimate, even if you don't know the exact numbers, for MicroMass and MiRaTA? How many people did you have working on the bus and the CNDH system?
Mm-hmm. So the bus and CNDH, right, basically call it one team. We actually had one guy working on software, comm, and avionics for MicroMass, which is nuts. But it was about 5 people, I think, the team working on the bus and CNDH and everything.
Okay. And also, have you thought of a method to implement the cross-link in your swarm?
It's a good question. And I think it'll basically be a simple radio. Probably fairly directional, so you can get, well, the thing that I'm assuming for this application is basically to state updates. So you don't actually have to trade that much information between the two. So it could be a fairly omnidirectional radio. And basically, it'd be a radio link. And which actually gets to an interesting question of how good of a crosslink radio do you want? Because if you can get a further distance, then that increases the connections in your network, and you possibly could do better planning based on that. And that's kind of a question I want to look into.
Other questions? Yes, wait.
I was just wondering, when you were talking about the constraints in the downlink and staying within the bounds and the algorithm figuring out, basically trying to stay in there, you were actually scheduling one and then another downlink. Would it be possible for the algorithm just to choose how many downlinks it needs and how often it would do it? It seemed like that would fall out.
Yeah. In fact, I guess I should have made clear that I was doing that by hand there because I don't yet have the algorithm fully implemented. But that's definitely the next step, to get that process of advancing through these steps, in the other order from what I'm going through them now, to be done automatically. And I mean, the problem is that you essentially have an infinite number of possibilities. You could include that downlink kind of anywhere, and you could explore a full tree of infinite possibilities. But we're guided by the windows that are available. So, that first downlink, that first blue line, that first downlink time, right here, if we introduce a downlink in that time, there's only really one place you can do it. And I think as long as, my idea is to take those windows and just kind of choose a random place within them to introduce a new activity.
Yeah. So I was wondering on the attitude control system that you're using, if it provides any software solutions for attitude and pointing, or whether you're doing it all in the PIC, because you said you're implementing a common filter. Yeah,
we're doing all of that in the PIC, actually. So we basically use it as at this point as a, I guess, complex interface. I'm not actually sure what level of algorithms they have on their ADCS unit for doing that, for doing estimation and control, but that's something that we wanted to be able to do ourselves. And so we just implemented all of that code on the PIC. And even doing that, we're at, I think, what is it, a third of our RAM usage. It doesn't actually take up that much processing power, fortunately.
That's great. Another question I had is, will you require any station keeping in the constellation, or are you just planning on synergistic, coincident orbits with your?
So my idea at this point is to just plan on synergistic, or I guess spontaneous timing of the events. But you definitely could introduce station keeping and maybe even positioning satellites closer together at choice, or moving them farther apart at choice. But at this point, I haven't really incorporated that in. But that would be something to incorporate in the future, definitely.
Do you have a propulsion associated with this system, or is that just attitude control?
With MiRaTA, to be clear.
With MiRaTA, right?
No, we don't. At this point, we thought it would be too complicated to add in propulsion, and we're already kind of packed in the bus and everything. And we don't really need it for our prime missions, so we don't have propulsion. But that would be something definitely interesting to add in the future.
If you're going to do station keeping.
Yeah, if we're going to do station keeping.
Just
definitely.
a string of pearls orbit.
Yeah.
Okay. I think we need to move on. So let me thank you very much.
Thank you.